What if I told you your workout isn't over when you stop moving? Your body keeps burning extra oxygen and extra calories thanks to something called EPOC. As well as it being the extra oxygen the body uses after exercise, it reflects the processes that restore balance, refilling energy stores, clearing metabolites like lactate, cooling the body, and supporting tissue repair. The harder or longer the exercise, the bigger and longer the EPOC. More intense work causes more anaerobic contribution and greater physiological disturbance, so the body needs more repayment in oxygen afterwards.
Hello and welcome. I'm pleased to say I've managed to find some more fantastic views to support the intro of the latest video. I think the steepness of these mountains set the scene for the content whilst we attempt to explain excess post-exercise oxygen consumption, more commonly referred to as EPOC. We'll take a look exactly what it is, why it occurs, and how exercise intensity and duration affect it. Also, we'll look at the recovery phase, which includes fast and slow components. Later in the video, we'll have a look at an interactive scenario for you to determine how coaches or athletes might consider EPOC. You'll be able to suggest some practical implications for training, and you can decide on some recovery strategies that they might use. If you manage to stick around until the end, I'll give you some sports science IA research question ideas specific to this topic, and you can have a go at the MCQs, DBQs, and the ERQs included in this video so you can maintain your exam readiness. With that being said, use the timestamps in the video to jump to the relevant sections, and now let's get stuck into the content.
The objectives you should achieve by the end of this video include being able to explain the phenomena of oxygen deficit and excess post-exercise oxygen consumption. Again, just the one objective to cover for this higher level content, but that means we can examine the fast and slow components as well as recovery in greater depth. At the start of exercise, the oxygen system can't instantly meet energy demand, so anaerobic pathways, including the phosphagen system and glycolysis, fill the gap. This is the oxygen deficit. After exercise, the body increases oxygen use, known as EPOC, to repay that deficit, restoring ATP and PCR stores, reoxygenating myoglobin and hemoglobin, removing CO2, and clearing lactate and other metabolites. Very short, very high power efforts rely mostly on the ATP PCR system and create a rapid but small deficit that requires fast replenishment. Longer, high-intensity intervals use more anaerobic glycolysis and produce more lactate and metabolic disturbance, so they produce a larger and longer EPOC. Both types raise post-exercise oxygen consumption, but the duration and size of EPOC depend on which systems and how much anaerobic metabolism were used. EPOC has two phases. The fast phase lasts only a few minutes, about 2 to 5 minutes. It exists because the body must quickly restore high-energy phosphates like PCR, reoxygenate myoglobin and hemoglobin, and bring breathing and heart rate back down. This rapid recovery is important when you need to repeat sprints or short maximal efforts. The slow phase can last from many minutes up to several hours. It reflects longer-lasting work, lactate being oxidized or used for gluconeogenesis, higher body temperature that raises metabolic rate, lingering effects of stress hormones, tissue repair, and protein synthesis. The more intense or longer the exercise, the larger and longer this slow phase becomes. Some sporting examples here would include something like a single 100-meter sprint, as it mainly produces a big fast phase as PCR is quickly restored, whereas a high-intensity interval training session or a marathon produces a much larger slow phase that can take many hours to settle back to baseline. After exercise, the body keeps using extra oxygen to restore balance. First, mitochondria make ATP to rebuild phosphocreatine so muscles can produce quick power again. They also refill oxygen stores in myoglobin and hemoglobin. Lactate made during hard work is removed using oxygen. Muscle and heart oxidize some lactate, and the liver can convert lactate back to glycogen via gluconeogenesis, both of which are O2-dependent processes. Elevated core temperature after exercise raises metabolism too, so cooling and circulatory adjustments increase O2 demand. Cells must restore acid-base balance and re-establish ion gradients like the sodium-potassium pump. These processes need ATP, so oxygen is required to make that ATP. Finally, immune activity and tissue repair via protein synthesis, use energy over hours, and add to the slow component of EPOC. How much each process contributes depends on the exercise. A short sprint mainly needs fast PCR recovery. A long run or heavy eccentric session causes more lactate clearance, thermoregulatory work, and tissue repair, producing a larger and longer EPOC. So after the initial content, here are some general factors which influence EPOC. Firstly, how big and how long EPOC lasts depends mainly on exercise intensity. Harder efforts use more anaerobic energy, make a bigger oxygen deficit, and produce a larger EPOC. Duration matters too. Even moderate exercise that goes on for a long time raises body temperature and metabolic disturbance, increasing the slow phase of EPOC. Fitness also changes the picture. Trained people have more efficient aerobic systems and faster PCR recovery, so for the same absolute workload, they often show a smaller EPOC. But because they can do much more work, very intense sessions still produce substantial EPOC. How you recover matters. Active recovery with some nice easy movements keeps blood flowing and speeds lactate removal and PCR resynthesis, usually shortening EPOC compared with complete rest. Environment and muscle mass also affect EPOC. Hot or humid conditions prolong the slow component because of thermal strain. Whole body exercise involves more muscle and therefore a larger EPOC than small muscle actions. As a final thought here, 2 sessions with the same total energy cost, a steady jog and a high intensity interval training session, will differ. The higher intensity session produces a larger EPOC because its high intensity spikes create a bigger oxygen deficit and greater metabolic disruption in comparison to the steady jog. In this section, we'll take a look at a hypothetical scenario for EPOC. Based on the content covered so far, can you design some evidence-based solutions to address recovery strategies and competitive performance for the given scenario? Let's see. Pause the video after the scenario is revealed and construct your answers. In this scenario, you are the designated strength and conditioning consultant working with a team of elite university swim athletes preparing for national championships. The swim coach has noticed that her swimmers are struggling with recovery between training sessions and events during competitions. The team trains twice daily with only 6-hour gaps between sessions. The challenge is for you to optimize recovery protocols to minimize EPOC duration and enhance performance in subsequent sessions and events within the constraints of training schedules and competition formats. Your task is to design evidence-based recovery strategies that address both fast and slow components of EPOC to improve training adaptation and competition performance. Let's take a look at the scenario specifics and the relevant data. Pause the video as it appears on screen. Construct your solutions and suggestions now. Possible solutions and suggestions for this scenario can be seen on screen now. This outlines the recovery protocol and breathing techniques, slow EPOC component management involving nutritional and temperature considerations. We can then see the potential training schedule modifications on the right-hand side of the screen. This includes session sequences and competition strategy. Then lastly, we can see how monitoring and assessment might look, including EPOC tracking, performance indicators, individual adjustments and expected outcomes, whilst attempting to improve performance. Okay, well done. Let's move on to some formative assessment and exam technique. In this section, we'll have a go at some quick-fire multi-choice questions based on the excess post-exercise oxygen consumption content, which may appear in paper 1A. Pause the video here, have a go and see how you get on. Let's take a look at the mark scheme so you can self-assess. Okay, good stuff. Next, let's have a go at some data-based, short answer and extended response questions, which may appear on paper 1B and paper 2, covering the EPOC content. For possible short answer and extended response style IB exam questions, you may be required to define EPOC and oxygen deficit, describe fast and slow components and mechanisms, and propose evidence-based recovery strategies. You may also need to use calculations and equations outlined in the sports science data booklet where necessary. On screen, you can see some short answer questions related to the video content. Use the command term key to carefully consider the requirements of each DBQ and ERQ question and construct your answers with the appropriate level of detail. Pause the video now and give them a go. Okay, let's take a look at the answers and see how you performed. Take a moment to pause the video here to reflect and self-assess. That is the end of the content for A2, hydration and nutrition. Next up is A3, response. We can finish by thinking about the following linking questions from the course guide between what we have covered in the last couple of higher level videos and topic A and C. A1.2, how might exercising in hot, humid conditions for extended periods of time influence the predominant energy system used and the lactate inflection point? And also C, 1.2, is there a relationship between mental toughness and the lactate inflection point? If you found the excess post-exercise oxygen consumption subtopic interesting, you may wish to pursue a scientific investigation in this area. On screen, you can see some sports science internal assessment ideas and key considerations you may wish to use to support with formulating a research question. To summarise, EPOC is the post-exercise elevation of oxygen consumption driven by PCR and O2 store restoration, lactate metabolism, thermoregulatory and repair processes. Intensity and duration are primary modulators. Use EPOC knowledge to optimise training design, energy intake and recovery prescriptions.
If you're a HL student or teacher, I hope you gained some value from the EPOC video today, and the interactive content makes the long-term memory kick in where it's needed. I'm still on the journey of introducing the channel to more PE teachers or students like you and supporting them with their IB sports science needs. So if you wouldn't mind, please do spread the word and get them to subscribe. Stay tuned for the next video where we'll take a look at the first piece of content from section A.3, which includes the importance of training design for safe and effective programs. You'll see why leading an active lifestyle supports physical well-being and how regular activity prevents disease, amongst other aspects. Alternatively, if you would like a little refresher on the previous content from topic A, I'd recommend looking at this episode right here. And thanks once again for watching, and I'll see you over on the next one.